Hello friends, I am Prashant V, Dhanshetti, Assistant Professor, Department of Civil Engineering from Walchand Institute of Technology, Solapur. Today I am here to explain about the numerical on stiffness matrix method of analysis. So the learning outcome for the today's lecture is students will be able to understand fixed end moments, degree of kinematic indeterminacy, stiffness matrix method of analysis, slope deflection equations. Now, any structure is designed for the stress resultants of bending moment, shear force, deflection, torsional stress and axial stress. The evaluation of these values or this moment and forces and plotting them for the structural component is known as analysis. And the determination of the dimension for the stress component and proportioning is known as design. Structure is generally classified in two categories: determinate structure and indeterminate structures. Determinate structures are analyzed just by the use of basic equilibrium equations. By this analysis, the unknown reactions are found for the further determination of stresses. Whereas redundant or indeterminate structures are not capable of being analyzed by mere use of basic equilibrium equations. They need some extra conditions like compatibility conditions of deformations to get the unknowns. So MA is equals to PB square A upon L and MB is equals to PA square B upon L. For beam with UDL over the whole span, we are having MA is equals to MB, that is WL square by 12. For UVL, uniformly varying load, so moment at A is WL square by 20 and moment at B is WL square by 30. Now the slope deflection equations. So if we consider a two span continuous beam, so this is L1, this is BL2. So we will have MAB, that is moment at fixed end is equals to, so MAB is equals to MFAB plus twice EI upon L1 into bracket twice theta A plus theta B minus 3 times delta upon L. So here this moment is at A and this MFAB is the fixed end moment. So that formula we have seen in the previous slide, and this 3 delta is this delta will be existing if there is a sinking of any support. So likewise MBA is equals to MFBA plus twice EI upon L1 into twice theta B plus theta A minus 3 delta upon L. So here we have to understand that if we are considering moment about this, so here about A, then theta A will be twice, and if we consider this the BA moment, here twice theta B will be there. So that you have to keep it in mind. Similarly we have MBC, that is for the span BC, this is MBC moment here at B joint and MCB moment at C joint. Now we will solve one continuous beam using displacement or stiffness matrix method, where EI is constant throughout. The loading is as shown in this figure. So the L1 span is of 4 meter, L2 span is of 3 meter. The first span is having 60 kilonewton per meter UDL over the whole span, whereas the second span is having a point load at the center, that point load is of 100 kilonewton. Now here the unknown displacement in these problems are rotation at B and rotation at C, that is the degree of freedom. So here the rotation is allowed and here also rotation is allowed. So we are having 2 degrees of freedom. So we will name it as 1 and 2. So first we have to fully restrain this members. So to fully restrain this member, we will apply the fixed support at B and C. So fixed end moments for a beam with UDL throughout its length is, so here pause the video and try to write answer on a paper. So the fixed end moment for UDL throughout the span is WL square by 12. So now we will find the fixed end moment for span AB, that is MFAB is equals to WL square by 12, that is 80 kilonewton meter, and MFBC is equals to minus MFCB, that is WL by 8, that is 37.5 kilonewton meter. So this MAB and MBA are same, and MBC and MCB are same. The forces, that is moment in this case, developed in the coordinate direction due to the given loads are. So the moment here, see, this moment is 80 kilonewton, this is clockwise, and for BC span 37.5 is anti-clockwise. So the load at this joint B is 80 minus 37.5, that is 42.5, and at this C, so it will be 37.5. Now we will assemble a slope deflection equation by giving unit displacement in the coordinate direction 1. So this coordinate direction 1, we will give a unit displacement. So this is the deflected shape of the beam. Then we will find the forces developed in the direction 1 and 2. So when we give a unit rotation here, so we will find out the forces developed in this direction 1 and in this direction 2. So here K11 at this point, that is the stiffness, will be equals to MBA plus MBC, that is moment at this MBA and MBC. So adding this moment, that is K11 is equals to 2EI upon L1 plus twice theta B plus theta A plus twice EI upon L2 twice theta B plus theta C. So here theta B is already known to you, that is unit rotation is given, whereas theta A and theta C are 0, as these are fixed support. So putting the values of theta A is equals to 0 and theta C is equals to 0 and theta B is equals to 1, we will get K11 value. So K11 will be 7 EI upon 3, whereas K21 means the moment at this will be 2 EI upon L2 into theta B plus twice theta C. So here we will get 2 EI by 3. Now second, now we will give a unit displacement to this second direction, and we will find the forces developed in coordinate direction 1 and 2. So again K12 is equals to MBC, so this moment MBC moment, so that is equals to 2 EI upon L2 into twice theta B plus theta C. Again here theta C unit rotation is given, that is equals to 1, and theta B is fixed, that is 0. Putting the values, we will get K12, that is 2 EI by 3, and K22 is equals to this one, so that is 2 EI upon 3 into theta B plus twice theta C. So here putting the values again, we will get 4 EI upon 3. Now arranging the stiffness matrix. So here as no external force is there, P matrix will be 0. Stiffness matrix equation is K matrix into delta matrix is equals to P minus PL matrix. Now K matrix is K11, K21, K12, K22. So we have already calculated this. Putting this value, we will get this matrix, and whereas delta 1 and delta 2 are unknown rotation, that is theta 1 and theta 2, and putting the value of PL, we will get this equation. So here we have taken common EI upon 3 into this K matrix into theta matrix is equals to force matrix. So solving this for theta 1 and theta 2, so theta 1 will be, that is theta B, and theta 2 is theta C. So solving this matrix, we will get theta B is equals to minus 11.875 upon EI, and theta C is minus 22.18 at upon EI, and theta A is equals to 0. Now to find the moment, total moment, we use the slope deflection equation, and putting the value of theta A and theta B in this equation, we will get MAB is equals to minus 85.938 kilonewton meter and MBA is equals to 63.13 kilonewton meter. In the same way, for the second span, we will have MBC is equals to, that putting the value of theta B and theta C, MBC is equals to minus 68.125 kilonewton meter and MCB is equals to 0. So these are the references which I have referred. Thank you very much for watching my video.